In this segment, we focus on reactions involving the addition of halogens such as Cl2 and Br2 across the carbon-carbon double bond of alkenes. We'll be comparing and contrasting this reaction with the other specific addition reactions that we've talked about before, such as the addition of HCl across a carbon-carbon double bond. So let's go ahead and dive in and take a look at this reaction, and much like with earlier reactions, we'll be looking at the overall reaction and walking through the mechanism to enable us to logically predict what the product would be of any reaction and to justify things like the regioselectivity or lack thereof and the stereoselectivity or lack thereof for these reactions. So let's go ahead and get started with a specific example of this reaction so that we can illustrate some of the highlights of the addition of halogens to alkenes. We'll start with our halogen starting material, which is our 2-methyl-2-butene. And we're going to react with, in this case, Cl2. We're going to walk through predicting what the product is that would result from this reaction, going step by step. So taking a look at the mechanism for this reaction to guide us toward the product or products that we would expect out of this reaction, we'll start by redrawing our organic starting material. I'm going to draw my chlorine, Cl2, in here. And keep in mind that the bond connecting the two chlorine atoms is a relatively weak bond, that bond I've shown in blue. And so it is pretty capable of breaking, taking the electrons from that bond onto one of the two chlorine atoms, like so. And that's exactly what's going to happen here at the first step of the mechanism, is that that bond is going to break as the pi bond comes over and attacks one of the two chlorine atoms. So the pi bond attacks one of the two chlorines while the other one breaks away so that we don't go over the octet rule. This step is largely enabled by the fact that that bond between the two chlorine atoms is a relatively weak bond. And we've seen that weakness of that bond in earlier chapters, specifically when we're looking at free radical reactions. We saw that that bond could break homolytically, meaning that one electron from the bond would go onto each of the two chlorine atoms. To give radical intermediates here, we don't see light and heat being present, and so the more favorable thing to happen is going to be that when you mix this with an alkene, instead the bond is going to break heterolytically, meaning that one of the two chlorines takes both of the electrons rather than them both getting the same number of electrons out of this. So we get that heterolytic bond breakage, and that's going to lead us to our first intermediates. So our first intermediates are going to be a chloride anion. So our negative charge on the chlorine, that's going to arise from that chlorine on the right that had 3 sets of lone pair electrons to start with, picking up a 4th set of lone pair electrons due to the breakage of that chlorine-chlorine bond. The other intermediate that results from this is going to be our carbon skeleton that will now have a new bond between one of the two carbon atoms and the chlorine atom. So we'll go ahead and look at what we would expect here. So that chlorine atom could form a bond to either the carbon on the left, like so, leaving a carbocation right here, or it could form a bond to the carbon on the right, putting our carbocation at carbon number, the second carbon of the chain. So, carbocation there, and chlorine atom here as an alternative. Now, thinking about what you know about carbocation stability, you can hopefully predict that the carbocation on the left is going to be the more stable of those two carbocations, because they are essentially equivalent other than the fact that one of them has a carbocation that is a tertiary carbocation, that's the one on the left. The one on the right is just a secondary carbocation. So therefore, the more favorable of the two is going to be this one on the left. And so that's going to be the major carbocation that we would expect to form here. This reaction mechanism is unique relative to the reaction mechanism where we're adding HCl across the carbon-carbon double bond and others, in that we can do a resonance type stabilization here as well. So we have a chlorine atom adjacent to on the carbon adjacent to the carbocation, and what can happen in those situations is a unique type of resonance situation where the lone pair electrons can come over from that chlorine atom and form a covalent bond to that carbocation to, in effect, make a three-membered ring intermediate. So we'll go ahead and do that here. So our chlorine atom originally had that blue bond tethering it to the chain. And we now have two sets of lone pair electrons here, and then the third set of lone pair electrons of the chlorine now has become a covalent bond to the carbon skeleton. So we have our chlorine atom. So our chlorine now, if we take a look at the formal charge on that, we're going to come up with a formal charge of +1. So by doing this resonance, what we're doing is sharing the formal charge over the chlorine and the carbon atom. And this three-membered ring or bridged structure here on the bottom, you might look at that and your gut instinct might be that that would be super duper unstable, because three-membered rings have a pretty unfavorable bond angles relative to what we'd expect for sp3 atoms. And so that might instinctively make you think, that's a really bad structure and we shouldn't draw that. But in actuality, this is a nice favorable resonance structure because of the fact that if we think back to what makes for a stable resonance structure, it has a lot of things going for it. So things that stabilize resonance structures were first and foremost the octet filled for the largest number of atoms. And what we would see here in this bottom structure is that we actually have the octet filled for every single atom in that molecule. So that's going to make that much more stable than would otherwise be the case. The second thing was that maximizing the number of covalent bonds stabilizes resonance structures. And you also see here that this structure on bottom has a larger number of covalent bonds than the one on top. So that's going to be another thing that works in its favor. So in actuality, it's going to be both of these structures that are significant contributors toward the actual hybrid structure. And then when we're talking about resonance, we're not referring to these structures rapidly interconverting between the two. What we're saying is that if we want to look at the actual situation of where the electron density is within this molecule, it would be a weighted average of these two structures. These are going to be the major contributors. That structure there on the right that I haven't put a yellow box around is going to be a minor contributor because that is the least stable of these three. So now what we'll do here is we'll move on to the second step of our mechanism, where I'm just going to go back here because I know that some of you like to have some words to describe what's happening in the mechanistic step. Step one was where the pi bond or the pi electrons attack the chlorine, the Cl2. So moving on now to the second step of the mechanism, now that we've made our carbocation intermediate, the second step of the mechanism is going to be that the nucleophile attacks the electrophilic carbon intermediate. Much like when we were doing the reaction with HCl, our first step was protonation, second step was that nucleophilic halogen anion attacking the electrophilic carbon. Similar things going to happen here. Our nucleophilic chloride is going to attack our electrophilic carbon. So taking a look at step 2 of the mechanism, we can use either of those two resonance structures from step 1 that are boxed off there in yellow as our intermediate that is going to be attacked here. I'm going to use the one that has the chlorine bridge, the three-membered ring, as the intermediate that I draw here, because that's going to be the one that's a little more challenging, I think, to show the electron pushing arrows for. So we'll go ahead and do that. But you could certainly also use that carbocation intermediate that's shown up top there in the yellow box as well here for this step. What you absolutely have to do, regardless of which of the two intermediates you choose, is you're going to have the lone pair of electrons from the chloride nucleophile come over, and it's going to attack at the more substituted of the two carbon atoms, so here and here. It's going to attack right here, and that's going to force the bond between the carbon and chlorine to break like so that we don't end up going over the octet rule. The reason that we prefer to attack that carbon atom on the right, the carbon that is more substituted, is because remember that we think of the electron density situation in the molecule as being a weighted average of those two resonance structures boxed in yellow. And so if we think of that as being an average, we would expect that the carbon atom on the right here is the more electrophilic of the two carbons. Because when we look at the two resonance structures and think about the actual structure being an average of those two, we see that in one of the two structures we do have a positive charge on that carbon. In the two favorable resonance structures, we never see a positive charge on the carbon on the left. So therefore, this carbon on the left side is less electrophilic, meaning less positively charged, positively polarized, has less positive character associated with it, and so it's not the favorable site for attack. Instead, that more electrophilic carbon on the right is where the chloride is going to attack. And you would see the same outcome if you had done the attack of the chloride directly on that carbocation that's the top structure in our two resonance structures. And again, you could use either one of those resonance structures here. It would be totally accurate to do so. Regardless of which of those intermediates you attack, you're going to end up with the same intermediate resulting from that, or the same product rather resulting from that. So let's go ahead and show that product. So we have our 4-carbon chain, and our 4-carbon chain I'll just highlight out for you here. 1, 2, 3, 4, and I've drawn that right over here. 1, 2, 3, 4, and then we sort out what's bonded to each of those 4 carbon atoms. So carbon number 2 of the chain, numbering from the right here, is going to be the carbon that has a methyl group bonded to it, as well as our newly bonded chlorine atom, like so. Carbon number 3 of the chain, numbering from right to left here in this case, is going to have that bond to chlorine as well, because when we broke our carbon-chlorine bond there in this step, that chlorine is still tethered to carbon number 3 of the chain right here. That bond never broke that we're showing in red. So that's the bond that's shown in red here as well. So this is going to be our final product that results from this mechanism. And we'll notice here that we've added the 2 chlorine atoms to the adjacent carbons of our alkene. That's always going to be the case, that the 2 chlorines are going to add vicinal. Vicinal meaning added to adjacent carbon atoms. So this we would describe as being vicinal. And specifically, it's a vicinal dihalide, where the di means 2, of course, 2 halogens on adjacent carbons. Vicinal means that they are on adjacent carbons. And so let's take a look at the stereochemistry of this particular reaction and the regioselectivity of this reaction. So first off, I'm going to ask you the question of, is this reaction regioselective? You can hit pause and take a moment to think about, would you describe this reaction as being regioselective? This reaction is not regioselective, and the reason why it's not regioselective is there's no way to make multiple constitutional isomers here. So regardless of which carbon atom of the chain gets which chlorine atom, we're going to make the same constitutional isomer one way or the other, because we're adding 2 identical groups here to the molecule. So we're adding a chlorine here and a chlorine here. It doesn't matter which chlorine you put on the carbon on the right and which you put on the carbon on the left, you're going to yield the same constitutional isomer one way or the other. The molecule is still going to have the same exact IUPAC name. So therefore, the reaction is not regioselective. And a general rule that we can point out for this is that, in general, when we are doing reactions where 2 identical groups are adding, for example, 2 chlorine atoms, 2 different hydrogen atoms, etc., the reaction cannot be regioselective, because those 2 groups, it doesn't matter which one you put on the carbon on the left versus the carbon on the right, you're going to end up with the same constitutional isomer one way or the other. So that addresses that question of regioselectivity. This reaction where we're adding Cl2 or Br2 across a carbon-carbon double bond will never be regioselective. Let's take a look at the stereoselectivity of this reaction now. And we have to take a look at and answer the question, first off, have we made any new chiral centers in this reaction? And the answer is yes, we have. Right here, where I put a star there, that is a newly created chiral center in this molecule. So we have to ask ourselves, is there a preference for R over S or vice versa? If so, the reaction is stereoselective. If not, the reaction is not stereoselective. And in this particular example, we would describe this reaction as being not stereoselective, because we would expect there to be an equal preference for placing that chlorine atom as either a wedge or a dash, meaning aimed forward or backward. Because when we're thinking about this second step of the mechanism, where the chloride anion comes in and attacks the carbon there, and that other chlorine pops up and breaks away, it can break away to the front of the molecule or the back of the molecule, giving therefore no stereoselectivity. So in actuality, if we're showing the stereochemistry of this reaction, you do need to remember to show both stereoisomers here, since the reaction is not stereoselective. So I'm going to show that chlorine atom as a dash, and I'm also going to show it as a wedge to show both of the stereoisomers that would result from this. Keep in mind that that other carbon atom that has a chlorine bonded to is not a chiral center, so we don't need to show wedges or dashes there, but if we did, we would make that wedges and dashes as well. So the reaction here is not stereoselective. So are there going to be any cases where the reaction could become stereoselective? The case where this could become stereoselective that we'll illustrate here is where we have rings, because rings are going to constrain the free rotation of bonds within the molecule. Let's take a look at that now. We'll walk through the mechanism for this reaction and use it as a tool to help look at the stereoselectivity that results when we have ring systems with the addition of X2 halogens. So let's take a look at this, and going through the mechanism here, the first thing we would expect to happen is that the bond between the two bromine atoms is going to break as it's attacked by the pi bond. So this is the same first step that we saw in the earlier reaction mechanism where we're adding Cl2 across the carbon-carbon double bond. So we take our pi bond, bring that over, it attacks the bromine. The bond between the two bromine atoms breaks like so, and that's going to result in the formation of our carbocation intermediate. And thinking about making the most stable carbocation that we can right away here, we want to put the bromine right here, because that will allow us to make a tertiary carbocation instead of a secondary carbocation. And our bromide anion that is broken away, I'll go ahead and write in here. And then we'll go ahead and do resonance. So for our resonance, that's going to take our bromine atom, bring over the electrons from that to make that three-membered ring bridge structure there. So we're going to have a three-membered ring that is fused to a six-membered ring here. So we'll go ahead and plug in our bromine atom. Positive formal charge goes on that like so. And our methyl group is still hanging out up there. And this is going to be a very favorable resonance structure due to the fact that we have the octet filled for all the atoms, and we have maximized the number of covalent bonds in this molecule. Another thing that I should mention here is that even if you wanted to do a carbocation rearrangement here to convert a secondary carbocation into a tertiary carbocation, there would never be a carbocation rearrangement, because we don't do carbocation rearrangements if the molecule is stabilized by resonance instead. So don't rearrange the carbocation when it's stabilized by resonance. And this is a general rule rather than one that's specific to this particular example problem or any particular example problem. Just if you make a carbocation and it's stabilized by resonance, don't try to do a carbocation rearrangement, because the carbocation rearrangement would end up making the molecule no longer stabilized by resonance, and resonance is more important than induction. So if the molecule has resonance, it does not need to do a carbocation rearrangement. So we've got our intermediates here, and remember that our goal here was to look at stereochemistry implications of having ring systems, particularly this six-membered ring, or a five-membered ring for that matter, whatever size ring you want, fused to this three-membered ring. The stereochemistry constraint that we introduce here is that when we make this three-membered ring, both of the bonds to bromine will absolutely have to be on the same face of the molecule. So either both have to be wedges or both have to be dashes. You can't have one and the other. So you can't have those two bonds to bromine, in other words, being trans to one another. The two bonds have to be oriented in the same direction. In other words, the two bonds have to be cis to one another. So we could also show it as an alternative like this. And I'll go ahead and fill in the full tetrahedron for both of these. So we have these two different enantiomer intermediates. And it's absolutely required that the two bonds to bromine there be in the same face of the molecule. And so that introduces, since these are major resonance structures, that introduces some constraints in terms of how the second bromine, the nucleophilic bromide anion, prefers to attack the molecule. The nucleophilic bromide anion is going to attack the intermediate here from the face opposite where the first bromine is bonded. So in other words, if bromine number 1 is bonded here using two dashes, shown in red, the bromide anion has to attack from the face opposite from that, the top face of the molecule, in other words. So the implication of that is what's going to happen is that the two bromine atoms will end up being trans to one another in the final product. That will be the preference, is that the stereoselectivity will be such that the two bromines are trans, because the second bromine has to attack the molecule from the face opposite where the first one lives. So in our second step of the mechanism here, our first step was that formation of the bond between carbon and bromine. Step 2 is that the nucleophilic bromide is going to attack. And remember that these three-membered ring resonance structures are very, very favorable. And to show what's really going on here in terms of the stereochemistry, then, we need to use those as our structures that are actually participating in the reaction at this next step of the mechanism. So I'm just drawing those two stereoisomer intermediates here, where we're showing that the bromine has to have two cis bonds leading to the rest of the molecule. Then we bring in the bromide anion. That's going to act as our nucleophile. So we bring that in here. And what's going to be the case is that in this top scenario, the bromine that is already bonded to the carbons is oriented toward the back of the molecule, and therefore the back side of the molecule is very sterically hindered. It's very crowded. And so instead, the bromide anion, the nucleophile, has to attack the molecule from the front side. So we'll have that bromide come in. It's going to attack right here from the front, and the reason it attacks that particular carbon, that's the more substituted carbon. So if we look back at those resonance structures circled up here in yellow, and think about which carbon atom is more electrophilic, it's definitely going to be that carbon there on top, because that's the one that has the carbocation character in our resonance set. So that's going to be the one that gets attacked here, and specifically that bromide anion is going to have to attack from the front face. It attacks from the front of the molecule as the carbon-bromine bond breaks right here to release that bromine, and that first bromine that was bonded there is still going to be bonded to the rest of the molecule as a dash. See that dash right there? We haven't done anything with that, so it's going to stay as is. On the other hand, the second bromine, the bromide anion that came in, had to attack from the front. So it's going to attack from the front, and it is going to end up being our wedge. So we'll end up with the two bromine atoms being trans to one another here. The same situation is going to be true on bottom. So on bottom, our bromide anion comes in. It's going to attack the more substituted carbon right there. That forces the carbon-bromine bond to break, so we don't go over the octet rule. And this bromide has to attack from the rear, or attack from the back side. And the reason it has to attack from the rear is because we already have that bridge to the bromine in front that's blocking access to the front side of the molecule. So as a consequence of this, we're going to end up with stereoselectivity here, where the two bromine atoms prefer to be trans to one another. So in the first case, the bromine that was bonded first is oriented toward the back side. The bromine that bonds second has to be oriented toward the front side. And that orientation of that bromine toward the front is going to push the methyl group there to the back. And then our other product here is going to correspond to that first bromine that was bonded, being a wedge oriented toward the front. And therefore the second bromine has to be a dash oriented to the back, and that's going to cause the methyl group to be oriented toward the front. So you'll notice here that the stereoselectivity of this reaction is that we prefer to make the trans product. And we've described this as being an anti-stereoselectivity. Anti means opposite, or you could think of it as being trans. And you'll notice here that the only products that we've made as the major products of this reaction, which I'll go ahead and put a circle on, correspond to the bromines being trans to one another. So anytime you're dealing with a ring and you're bringing in the two bromine atoms, due to the fact that we have that three-membered ring intermediate, that's going to force the reaction to be stereoselective, and specifically it's going to have anti-stereoselectivity. So this reaction, just like the earlier reactions we looked at where we're adding Br2 or Cl2, are not going to be regioselective. There's no preference for one constitutional isomer over the other, but there is a preference for these specific trans stereoisomers. And another way you could look at this is you could think about the 2 to the n rule. So the 2 to the n rule says that we take 2 to the n, where n is the number of stereocenters. And specifically, we're looking at the newly created stereocenters here. And you ask yourself what 2 to the n will equal, because that gives you the maximum number of possible stereoisomer products that could hypothetically form. And if the actual number is less than that theoretical number, then the reaction is stereoselective. So in this case, for example, 2 to the n would give us 2 to the 2, because there's 2 stereocenters in our newly formed product, which would mean there's 4 hypothetical possible stereoisomers that could result from this. But in actuality, we only make 2 of those 4. We make the 2 that I've circled in blue here, the 2 that correspond to having the 2 bromines anti. The 2 other hypothetical products would be the ones that would have the bromines cis to one another. And we don't see those being made in this reaction as major products. So therefore, the reaction is stereoselective. So the takeaway from this example problem that you can generally look at is that the stereoselectivity for this particular reaction arises from the fact that we have a cyclohexane ring, which constrains the overall conformation of the molecule because we don't have total free rotation around the carbon-carbon bonds of that ring. In other words, it prefers the chair-type conformation. And moreover, the fact that we have that bridged intermediate, meaning that 3-membered ring that has the bromine or the chlorine as part of it. And that bridged intermediate has to be locked cis, meaning that the 2 bonds to bromine or 2 bonds to chlorine are cis. And that ultimately then is going to cause the second bromine atom that comes in and attacks to attack from the face opposite that, giving rise to a preference for the trans products here. And this is only going to be the case for these types of situations where we have this 3-membered bridge present, because that 3-membered bridge is what's going to introduce that extra level of constraint into the reaction. So if we had just a typical carbocation intermediate here, and there wasn't that 3-membered bridge that could form by resonance, then we would not have stereoselectivity being introduced here. But the stereoselectivity comes from that 3-membered bridge that is present. Has to be one of the components of a reaction that will have this stereoselectivity taking place.